Okay, so we talked a good bit about acidity, and we've hinted in previous conversations about the power that we have to predict equilibrium position with the factors that we've considered. Now let's practice it. All right, before we do, let's review that when you have any acid-base reaction, where you have an acid here, a marker, this is an acid, right? And here's its conjugate base. When you have any acid-base reaction, there are two distinct ways to predict which side is favored. Number one, you can consider the pKa values, right? And these, by the way, go together, okay? So you can consider the pKa values of either side, right? So whichever one is lower, let's just make up some numbers here. Let's say the pKa of this guy is 5, and the pKa of this one is, let's say, 15. Then this is going to be the better acid, and it's going to go in that direction. All right, so that's if we use method number one. If we use method number two, we're going to have to look at the structures of these two conjugate bases and see which one's more stable. Now, the more stable one, of course, is going to be the base of the better acid. All right, so let's practice that. I'm going to do it both ways. So first of all, I'm going to do it with the pKa values of HA and HB. All right. So let's look at this question. Predict the position of equilibrium for the following reaction. So I've got some amide, which you don't necessarily recognize, right? But I'll tell you that that's an amide. And here I've got something that's like an amide, but I don't know what it is, right? Look at that. It's sulfur instead of oxygen. Okay, so there's the difference. And over here, so it looks like everything's the same here. Looks like this compound is the same as that one, except it's got oxygen, right? These two are the ones that looks like we're going to be considering. So this appears to be, let me go with another color here for a second. This appears to be my AH, right? Where this is all my conjugate base, and there's my hydrogen, right? And here's my BH, right? So can you see AH? And here's, if I strip off that proton, I'm left with A minus, right? And I start out with some other compound, some base, let's call that B minus. And when I put a proton, it becomes BH, okay? So this is common notation for the reactions. Let's go back and see, we just did it on the previous slide, right? AH and B minus, A minus, and HB, right? So this is an example of that. All right. Now, having said that, let's look at this. Let's go back to blue, and let's say, aha. So we're going to use the pKa's. Well, I don't know the pKa's of this compound right here. Can't look it up. But I can see that if I make a resonance structure, watch this, I'm going to have resonance with something that looks like that, right? Okay? So this does look familiar. That looks familiar. Okay, so it looks like it's the conjugate base of SH, okay? Right? You know how we go SH? It's the conjugate base of SH, which is an acid, but a weak acid, okay? Now, or let's see, SH, right? Something like that, okay? Now this, let's come over here and do the same thing. This I see, I can do resonance with that also. This can go here, and that can go here. And so this appears to be right. Okay, I realize I haven't drawn all the details here, but let's keep it like that, okay? Because this is what I'm looking for, right? It's this. Now I'm comparing that, and that appears to be the conjugate base of an alcohol, right? So I know the pKa of an alcohol, it's about 18. And the pK of SH is higher. I forget how much higher, but I'm going to look it up. That's not one I have. That's not one of the ones I have memorized. I'm looking up the pKa of SH. pKa of SH. And I showed it earlier on one of those tables. It's higher. Where is it? pKa of SH. Should have had that on hand. All right. You know what I'm going to do? I'm going to Google it. pK of CH3SH. Let's try that. 10.4. Wait, that's lower. Oh, yeah, that's lower because it's a more stable base. That's right, exactly. Okay, said that backwards. All right, so it's actually lower. So it's about 10, right? So you can see, like, this is almost a billion times stronger of an acid. So since it's a stronger of an acid, this is more stable of a conjugate base, right? A stronger acid is going to give you a more stable conjugate base. And since this is more stable, this is all part of that, right? Since this is more stable, we know the reaction is going to go that way. All right? So again, what we did was we recognized, after we considered what's going on here, we saw, oh, I can get something that looks like that. And that I can relate back to a pKa that I know. I had to look that up, but this one I know, right? Okay, so that's one way of doing it. The reaction goes this way. Now let's do it another way. Okay, remember now we were going to do. This is the first one I just did. We looked at we looked up the pKa values and found which one was favored. Now let's say we can do the same thing, but we can do it by looking at the relative stability of the bases B minus and A minus. I think you're going to find that these ways are actually equivalent, okay? So let's go here, and remember we had that acronym for this. The acronym was ARIO, atom, resonance, induction, and orbital, right? So the atom that this is bonded to, it turns out, let me go back to blue here, that they're both bonded to nitrogen, right? So that's not going to help us, okay? But let's consider the resonance. That might be good something, and we did this in the previous slide. That goes here, that goes here. Okay, and this one goes in a very similar resonance, right? You can see you're going to have to get good at these resonance structures, or else you're going to be really getting drugged through the streets. It's like water skiing without skis, getting drug on your belly. That's how it feels if you don't understand these curved arrow notation, okay? So now I go, okay, now I'm going to have to appreciate how stable that is compared to how stable that is, okay? So if I look at, I used resonance, now I'm actually going to go back to the atom again, right? Because I can now consider the stability of that atom over the stability of that atom. So I say this is a bigger atom, and you may recall that we've got two factors for that. Electronegativity and size. I should have put size first because size actually is the bigger of the two. Okay? So it turns out sulfur's right below oxygen. It's got an extra shell on it, so it's a lot bigger. Sulfur is a lot bigger than oxygen. And so it turns out this is more stable. So since that's more stable, I'm going to put a star next to it like that with my pen, and I'm going to say the reaction goes this way. Okay? Well, actually, we didn't consider, we used resonance, but since they both have resonance, that's not the key. It's not resonance because they both have it. It turns out to be the atom. Once we found the resonance structure, we found it was the atom. What about induction? Well, induction doesn't have anything to do with it because there's no electron withdrawing groups pulling electrons off, and they both have the same orbitals. So it turns out because of the atom, that is the atom of the resonance structure, we found that this structure was more stable. The reaction comes this way, and we got the same answer as we did the previous time. All right, that's a complicated question, but it brings a lot of things together. So if you don't understand that, I ask you to consider pulling out a piece of paper, starting the video over again, and predicting where I'm going to go with it. I think you'll see it is a nice, clean story, and when you get it, you're going to go, oh yeah, this is not so bad. All right, good luck.